600 megaparsecs, that might be 300 megaparsecs, and that might be 300 megaparsecs. Okay? So this is with flat spatial sections. With flat space sections, it could be a torus. How do you get a torus? You simply identify those two sides. You identify the front and the back, and you identify the top and the bottom. You identify them. So it then becomes like Pac-Man. You walk out that edge, and you walk in the other side. Okay? And it is possible that the universe has such a compact topology. Now, the point about this is the following. The Einstein equations give you the local geometry. They do not tell you the global connectivity, the global topology. And the flat space sections are just as consistent with Einstein equations as a torus. Now, if you lived in a toroidal universe, what would it mean? It would mean light from our galaxy would exit there and re-enter here. It would mean we would see our own galaxy over there, and over there, and over there. We would get many images of our own galaxy in a toroidal topology. And these are what we call small universes. A small universe is one in which we are able to see right around it since the decoupling of matter and radiation. And in a small universe, we will see many different copies of the same galaxy. So you might say, that's easy. Why don't we just look around and see if we see many images of the same galaxy? Well, why is that difficult? Well, because our galaxy is a typical galaxy. There's 10 to the 11th other galaxies out there. Suppose there was 1,000 images of our galaxy out there. How would you tell that it was our galaxy rather than a different galaxy? You would find it very, very difficult. The position is like, in this room, if we had glass on the ceiling and the floor and all the walls, you would see yourselves stretching away for infinity. The further ones would be dimmed by reflection in the glass. They would look much smaller. In the case of the universe, there's redshift effects and so on. And also, if you look at the different ones, you see yourself from a different direction. You would see your eyes in that direction, and the back of your head's in that direction, and the top of your head's in that direction. You would see yourself from all sorts. Yeah.
Sorry, how's that different from going this way and arriving back from the other side? In the previous model, in a closed universe.
That's what. How's it different? Oh, it's the same.
Okay, so you can have the same effect as the closed universe.
Yes, yes. Excepting the closed universe with the standard dynamics, the light doesn't have time to go around. In the standard dynamics, in fact, it's very finely balanced. In the K is +1 models, in principle, you're quite right. But the problem is the time for light to traverse the universe is exactly the same as the age of the universe. So in those closed universes, we don't see around because the universe hasn't existed for long enough. Good question. So in the closed universes, if you had a static universe, Einstein's original static universe, then you had a sphere and the universe wasn't expanding. In that, we would have seen ourselves millions and millions of times because light could have traveled around millions of times since the beginning of the universe. In an expanding one, it's just delicately balanced. So just at the time you would have seen around, you hit the Big Bang and there isn't time for the universe light to go around. Okay, so what I'm saying is the following. K is +1 implies compact. K is -0, -1, it is possible to be compact or to be finite. And you may have seen in Nature about 6 weeks ago now, there was a suggestion, faint suggestions from the microwave background that our universe could be closed in exactly this way. Let me say the following. For the case K is +1, there are alternative topologies also. There are also alternative topologies in the case K is +1. The natural topology of the sphere is you set off here and then you arrive at the antipodes, you keep going and you arrive back. Now what's the simple alternative? The alternative, the simplest one, is when you arrive back at the antipodes, it isn't a different point, it's the point you started off from. That's a possible topology of the sphere, that each antipodal point is the same as the one you started from. Okay, now what I've done is I've spent quite a bit of time on the geometry of the universe and a little bit of time on its topology. I think that's about enough on that, except to say the final comment on all of this is that this is a very special situation. If, as a cosmologist or a relativist, you imagine universe models, all sorts of possible universes, what fraction of them would have this geometry? And the answer is a negligible fraction, because this is such an incredibly special geometry. And so one of the puzzles for cosmologists, most cosmologists believe that this is the geometry of the observable part of the universe. And I'll talk about limits on observations later on. So everybody believes this is a very good model. Well, not exactly Robertson-Walker, more or less. You've got this averaging scale. On smaller scales, it's not. But up to this scale, yes, Robertson-Walker. So the question which comes is why? Why on earth should the universe in which we live have this extremely special geometry, which is now being suggested by this metric tensor, with this universal cosmic time and with isotropy everywhere? So this is one of the puzzles which people have been looking. There are two schools of thought about this, and we'll come back to them later on. One school says, look, in general, we expect things to have a generic kind of behavior, and you write down random universes. This is infinitely improbable. And so we need to explain. We need to explain why. And the explanation is the theory of inflation, which I will talk about and other people will talk about later on. The idea that people now have, there's a theory called inflation, we'll talk about it later on, which tries to explain why the universe is as it is. But there's another school of thought which says, why not? Okay. In the old days, we didn't find it strange that the universe was special. This is the way it is. The mechanism that creates universes likes special universes. Okay? God likes special universes, nice symmetries, or whatever. Quantum field theory likes special universes, whatever it is. So, one group of people are asking why, but there's a small group of people who say the opposite, why not? And there is an interesting gloss on this. One of the underlying questions in cosmology is, why does life exist? Now, you may or may not think that's a question of cosmology, but if you pursue cosmology for long enough, one of the questions cosmologists want to answer is, why is the universe such that life can exist? And you can make a bit of a case that if the universe is not like a Robertson-Walker model, then life will not exist. So that's something I'll come to towards the end. One may be able to partly say one of the reasons the universe is isotropic and homogeneous is because it's very difficult for life to exist if the universe is not almost homogeneous and isotropic. Right. That was section 1. Section 2. The geometry of the universe. Now, 3. The size of the universe. Which I haven't mentioned so far, but we need to distinguish the universe or the observable universe. When people write about it, they often confuse these two things quite badly. The size of the universe is infinite if k is 0 or minus 1 and the natural topology. You now understand that we have to add that criteria. So in a sense, so what's the size of the universe? If k is 0 or minus 1 and the natural topology is infinite. Well, people don't talk about it. When people talk about the size of the universe, what they're usually talking about is the size of the observable universe, what we can actually see. So please don't confuse these two things. They're quite different. Okay, well, this is about the scale of the inverse Hubble constant. we can see out, I'll talk about this later on, but basically we see out on our light cone, which goes back into time, and then the distance we can see stops when we reach the time of decoupling, which I'll mention because at earlier times the universe is opaque. We'll come back to this in half a minute, but at very early times, follow the universe back, its temperatures go up. In the present universe, matter, atoms are atoms, but as the temperature goes up, they get ionized. The electrons get split from the nuclei because the temperature goes up so much. And so at very early times, the universe is opaque. How long do you want me to carry on for? Huh? Okay. Okay. The visual horizon is the distance we can see in the time allowed. The time light has to travel to us is not the time since the beginning of the universe, it's the time since decoupling. Because that's when the universe became transparent. And so following the universe back, at a time of decoupling, the universe became, which corresponds to a temperature of about 4,000 degrees Kelvin, the matter was ionized. That's ordinary physics. Once it's ionized, the universe is opaque because of Thomson scattering. So the universe was opaque and it became transparent. How far can we see out? Well, it's about the scale of the inverse Hubble parameter. And that is about 10 to the 10 light years. So the visible part of the universe is of the order of 10 to the 10 light years. Within that scale, there's of the order of 10 to the 11th galaxies we can see, which means there's of the order of 10 to the 22nd stars in the part of the universe we can see. Now, our scientific notation makes it easy to write this down. 100,000 million galaxies, each containing 100,000 million stars. How many planets are there up there? Wow. Any guesses how many planets? Well, let's take a guess. 10 to the 26 planets. So how many people up there are there looking back at us? Well, it depends on the fraction of habitable planets, but 10 to the 26 planets, that's a heck of a lot of planets. Unless there is something unbelievably special about this planet, there's a heck of a lot of other things, people, whatever, up there looking back down at us. How many inhabitable planets? Who knows? Given these numbers, I could easily make a case for at least 10 to the 10 habitable planets up there. Sorry, this number was wrong, 10 to the 26 planets. Sorry, that should have been about 10 to the 23. So, what we've got then is this huge size, 10 to the 10 light years, and this huge number of galaxies, this huge number of stars up there. So a question which arises is why? Again, why is the universe so big? And this again is something which we say a little bit about later on, but it has enormously important implications for observations. Here we are on our planet up there, looking out at the universe. Now, let's say we get gung-ho about astronomy. Let's say we're going to set up a computer database and we're going to collect data for the next 10,000 years and analyze it in order to see the changes in the universe. So we start collecting the data up there and we look for 10,000 years. When will we be 10,000 years from now? The answer is we'll be at the same spot in the history of the universe because of the scale of 10 to the 10 years. If we set out in a spacecraft today, traveling at the speed of light for the next 10,000 years collecting data, so we're moving sideways from here and we're trying to collect data, where will we have got to? We won't have left that spot in the universe. In other words, because of this immense size of the universe, we can only see the universe from one space-time event. And that is one of the most fundamental features of observational cosmology. On the Earth, You can look and the horizon cuts you off. So you travel to the horizon and you look beyond the horizon. In cosmology,